So at the end of the last week's session on the PrimeCheck application, we had talked about an overview of the PrimeCheck app case study. We'd also kind of talked about the high-level view of the server components, talking about the PrimeCheck controller and the PrimeCheck service, and then how the PrimeCheck service forwarded to the appropriate PrimeCheck strategy, and so on. And now that we've talked about this at a high level, we're going to start zooming in and seeing how to actually implement the server components. So you get a chance to see how to implement the server controller, server service, and then the various strategies that implement these with different concurrency models. And as always, you can get this in my GitHub repository, in the EX1 project, in the web MVC folder, in the live lessons GitHub repo. So here we are in the EX1 folder for the PrimeCheck app, and we're going to zoom in and focus on the server part of this. So this is the entry point into the microservice. There's a single microservice here, which embodies within it or encapsulates within it several different services or service implementation strategies. When we get to the next part of the course, which we'll probably start next class, we'll start talking about how you could actually have multiple microservices to do the same thing, but I didn't want to have to introduce that topic quite yet. So here's what the PrimeCheck or PC server microservice entry point looks like. It's this PC server app, and you can see it goes ahead and parses the command line arguments, if there are any, and then runs the application, which causes Spring to do all the auto wiring and dependency injection and so on and so forth. You'll also note, as we've been doing for the last couple of assignments, we're configuring Spring so that each incoming request from a client is going to be mapped to a new virtual thread. So unlike the traditional Spring approach and what you get if you don't do this configuration, this customization, you'll have just a pool of threads and they'll run and each request comes in and works in the pool of threads until the thread pool is all being used, and then things just get queued up. In this model, each incoming request is mapped to a new virtual thread using the executor's new virtual thread per task executor factory method. And these are just some kind of cut and paste beans that are added to make sure that things are initialized properly. OK, so leaving that aside, now let's go take a look at the PC server controller. This looks pretty much like what you'd expect. It's got an application context. It's not really clear at this point why we have an application context, because we don't need it, but we have one anyway. Doesn't hurt anything. And then we have a PC server service, which is auto-wired to point to the service implementation. And then down here, you can see that we have a couple of methods. We have one called checkIfPrime. checkIfPrime is defined with the checkIfPrime mapping for the route name. And we take an integer strategy, which is going to be either, say, the structured concurrency strategy or the parallel stream strategy or the completable future strategy or whatever. And then we take the prime candidate, which we're going to check for primality. And as we always do in our code, we just sort of forward that down to the underlying service to do its thing. Similar kind of approach here with the checkIfPrimeList method, which also has a routing name. And the main difference is, in addition to taking a strategy, which it needs so it can forward to the right implementation, it also takes a list of prime candidate integers. And we have to designate that with the @request_param so that Spring knows this is a parameter to fish out of the incoming HTTP URI. And then we also pass another parameter, which is going to be whether or not we want this code to run in parallel. And you'll see we can tweak running things in parallel or sequentially when we look at the implementations. So that also just forwards down to the service. So let's take a look at the service. The service is also pretty clean and lean, or lean and mean. It has a service annotation just saying to Spring, make sure you can auto-wire this stuff together. It's got an array of PC abstract strategy subclass instances. So you'll notice here we have an array of 3 instances. The order matters here. You have to keep them in the right order, because that's what the client's going to be passing in to indicate which one to run. And so we have basically structured concurrency, parallel stream strategy, and completable future strategy. Those things are all put in there. There are other ways to do this. I could have used a map, and I could have encoded things with a symbolic name. I just used an integer just for kicks. So down here, we have the checkIfPrime strategy method, and you can see all it does is it takes the strategy parameter and indexes into the strategy array, which fishes out whatever the corresponding subclass of PC abstract strategy is, and it invokes its checkIfPrime method and forwards the prime candidate. So this is just essentially forwarding to the underlying implementation strategy. Same thing holds true for check if prime list, where again we index into that called the check if prime list and pass in the prime candidates and the Boolean parallel flag. So this is where things get interesting. So let's go ahead and take a look at a couple of different implementation strategies. So let's start off with a pretty simple one. This is the parallel stream strategy implementation. You can see it implements PC abstract strategy, so it has that API. And then down here, PC abstract strategy, you should probably start with that one. PC abstract strategy, as you can see, it has a method called check if prime, and the check if prime method takes the prime candidate and calls a helper method called isPrime, which checks to see if the number is prime. We've looked at this code many times, so I won't spend a lot of time on it, but it basically takes the prime candidate, returns 0 if it's prime, and it returns a value greater than 0 if it's not prime, which is its smallest factor. And it also prints out a little diagnostic. So that's pretty simple. Then there's also this other method, which is basically abstract. So you can see that this PC abstract strategy is defined as an interface. So it's an interface, and it's given a default implementation. That's one of the cool features that came with Java 9, or Java 8 rather, was the ability to have interfaces contain default implementations of methods. But then the check if prime list method is not given a default implementation, and we expect each of the implementations of PC abstract strategy to override that. So you can see what we do down here. Here's the check if prime list method, because that's the only one we need to worry about since we're inheriting the check if prime method from PC abstract strategy, because it's not running in parallel. And so down here we take in the list of prime candidates and the flag that says, do we want to run in parallel or not? And then we use a really clever little trick that you can use with Java Streams, where we say, hey, Java Streams framework, please take this list of prime candidates and get a splitterator to it. A splitterator is basically an iterator on steroids, and it's going to allow the Streams framework to convert this list into a stream. And you can pass in a flag to the streamSupport.stream method indicating whether you want this to run in parallel or not. In this particular case, we want it to run in parallel. So, or whatever the client said. So if this is true, this will be a parallel stream. If this is false, it'll be a sequential stream. And then what we do is for each item in the stream, either sequentially or in parallel, we're going to go ahead and apply the map intermediate operation to check each of those integers to see whether they're prime. And again, that'll either run sequentially in one thread if we have the sequential stream, if parallel is false, or if the parallel flag is true. All these calls will run concurrently in the common fork join pool. Not in virtual threads, but in the common fork join pool. And then after we're done, we trigger the computations and we collect the results into a list, which will be a list of integers, which will be indicating whether they're prime or not. And then we can display the results if we're debugging, and we return the results. So that's all we have to do for parallel streams. I really like parallel streams for simple types of code like this, because I find it incredibly concise. Once you understand the functional programming paradigm, I find it very expressive and easy to understand. And it basically says, make this into a stream, either parallel or not. And then for each item, go ahead and compute whether they're prime or not, either in parallel or not, and then collect the results into a list. Very, very, very concise, very, very simple. OK, so that is the PC parallel stream strategy. Let's take a look in contrast at the structured concurrency strategy. So this approach is going to use the executor's variant of structured concurrency. It's not going to use the approach that uses structured task scope. It's going to use the sort of a little bit older version. But one of the nice things about this little bit older version, it's really easy to switch between single-threaded and multi-threaded execution with just one little conditional expression, much like what we did with parallel streams. So here's the implementation. I guess I should point out first, once again, that PC structured concurrency strategy implements PC abstract strategy. So it gets the check if prime method for the ride. And then here's the one that actually checks to see if the list elements are prime in parallel or not. And so you can see what it does. Because we're doing this with structured concurrency, I decided just for kicks not to use streams at all here, just to use the older school Java 7 style. So we have to make our own array list, which is an array list of futures to integers. And then we go ahead and make a new scope, which is going to be the executor service scope. And it's either going to be the virtual thread per task executor, if parallel is true, or if the parallel flag is false, it'll be the new single-threaded executor, which just runs everything in a single thread of control. So in either case, we've got an executor service instance we call scope. Probably not the best term, but what's wrong with it? It's not too bad. And then for each item in the prime candidates list, we're going to go ahead and submit a task to run either sequentially or in parallel, depending on what kind of executor service we made. So let's, for sake of argument and without loss of generality, let's assume we're using the parallel version, the new thread, new virtual thread per task executor. So when we submit this task, which checks to see if the value is prime or not, is going to run in a new virtual thread because we created the executor service to be the new virtual thread per task executor. And the result that comes back from that, of course, is a future to said task. And that future is going to be added to the results. So the results will continue, just blop, 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 as we run through there. They'll be putting futures to tasks. And then what happens here is we're going to go ahead and create a response from this. Also, I should note here, notice we have this try catch block sort of nested inside of the method. So what that says is basically, I guess I should make this more clear. This scope will not be exited until all the tasks complete. So until all those virtual threads that are running, until they finish doing their thing, that try catch block won't be exited unless an exception occurs, in which case we bail out. But let's assume no exception occurs, all the tasks will complete. And then at that point, we're going to go ahead and use a little helper method here called futures to objects, which is going to convert the list into a stream. And then it'll go ahead and take each of the futures and turn it into an object in the stream. We'll eradicate anything that's null. And then we make a list of those results. So that will end up giving us this list of futures to the results, because we have to do that when we're dealing with structured concurrency models, because they have lists of futures to things. We want lists of things. And then we return that result or that response from the method. OK, so that's the other way of doing things. Now, I'll kind of do the comparisons as we go along. So again, for my money, I like the conciseness of parallel streams. I just think it's super streamlined. You can get the same ease of swapping back and forth between concurrent and non-concurrent execution. And there just is less ceremony there. With the structured concurrency model, admittedly, this is actually the one that's a little bit simpler. This is the one that's the executor service version. There's just a bit extra stuff going on. And it's not that much extra stuff, but it's just a little bit extra stuff. So you can decide what you like. So the key thing to come away with from this example of the server implementations are the differences between the structured concurrency implementation that uses executor service variant of structured concurrency and the parallel streams model. And again, to me, I find parallel streams more concise. We'll, of course, find out which one runs better when we actually run the performance tests, but we'll do that in just a little bit.